There's a machine in California that has to be kept colder than deep space itself. Not because it is dangerous, but because if the outside world interacts with it even slightly, the quantum state inside begins to collapse. According to the narration, this is what makes the story so unsettling. Quantum artificial intelligence is not simply delivering faster computation. It is forcing us to confront one of the oldest unanswered questions in physics. What does reality do before it is observed? Inside a quantum computer, particles can exist in multiple possible states at the same time. But the moment information leaks into the surrounding environment, those possibilities collapse into a single definite outcome. Machines such as Google's Willow are transforming that mystery into practical technology. And the deeper researchers investigate, the more it appears that the solid world around us may be only the visible surface of something far stranger beneath. At the heart of a quantum computer is not a massive engine but a tiny chip filled with qubits. Unlike the bits used in conventional computers, which can only be either 0 or 1, qubits can exist in a superposition of both states simultaneously. According to the narration, this unusual property is what gives quantum computers their extraordinary power. When many qubits become entangled, they can explore an enormous range of possibilities that classical computers cannot realistically process. Yet there is a significant challenge. Superposition is extremely fragile. A slight vibration, a stray photon, or even a tiny electromagnetic disturbance can destroy the quantum state. That is why these machines must be cooled to temperatures even colder than the space between galaxies. For a brief moment, the computer creates an isolated environment where the outside universe is almost prevented from interfering. Within that silence, the qubits are able to perform calculations while reality has not yet settled on a single answer. The narration traces this mystery back to the famous double-slit experiment, one of the simplest yet most unsettling experiments in all of physics. When particles are sent through two slits without anyone measuring which path they take, they produce an interference pattern, behaving as though each particle somehow passed through both slits simultaneously. However, when a detector is placed to determine which slit the particle actually traveled through, the interference pattern disappears, and the particle behaves as though it chose only one path. According to the narration, the truly disturbing aspect is that the crucial difference is not a physical collision but the presence of information. When the universe has no record of the particle's path, it behaves like a wave of possibilities. When that path becomes known, those possibilities collapse into a single outcome. This phenomenon is known as the measurement problem. Even after nearly a century of research, physics can predict these outcomes with extraordinary precision, yet it still cannot fully explain why one definite reality emerges from so many possible ones. Albert Einstein believed that particles should possess definite properties before they are measured. The idea that reality becomes definite only through observation seemed incomplete and deeply unsatisfying to him. He argued that there must be hidden information beneath quantum mechanics, a deeper layer that determines what particles are actually doing before anyone observes them. The narration explains that physicist John Bell later transformed this philosophical disagreement into a scientific test. If particles carried hidden instructions, their behavior would have to obey specific mathematical limits. Quantum mechanics, however, predicted that entangled particles would violate those limits. When experiments were eventually performed, the results repeatedly agreed with quantum mechanics. Again and again, entangled particles displayed correlations too strong to fit Einstein's classical expectations. According to the narration, this suggests that reality at its deepest level is not organized in the intuitive way common sense would predict. The narration argues that this mystery is about far more than strange particles inside laboratory experiments. It implies that the solid, familiar world humans experience every day may emerge from underlying rules that are themselves neither solid nor familiar. Google's Willow quantum processor, according to the narration, has brought this long-standing mystery into the age of quantum artificial intelligence. It demonstrated that delicate quantum states are no longer merely laboratory curiosities, but systems that engineers can control on a meaningful scale. Equipped with 105 qubits, improved coherence, and significant advances in quantum error correction, Willow reportedly showed that quantum systems can actually become more stable as they grow larger, an important milestone on the path toward practical quantum computing. The narration highlights Willow's benchmark performance, in which it completed a specialized calculation in minutes that would require an unimaginably long time for a classical supercomputer. While this achievement does not prove the existence of parallel universes or solve the measurement problem, it makes the underlying questions increasingly difficult to ignore. If a quantum computer truly relies on superposition and entanglement to explore an enormous landscape of possibilities, then what is actually happening inside the machine while those calculations are taking place? According to the narration, the uncomfortable truth is that the mathematics works, the machines work, and the predictions work, but the deeper meaning remains unresolved. That, it suggests, may be the most unsettling revelation of quantum artificial intelligence. Humanity is beginning to build future technologies upon aspects of reality that can be used with astonishing precision, yet are still not fully understood. The narration concludes by emphasizing that quantum behavior is not confined to laboratories or limited to machines like Willow. The same quantum rules are operating continuously within the atoms of our bodies, the air around us, and the light passing through the room. Our hands feel solid because they are constantly interacting with photons, air molecules, heat, surfaces, vibrations, and countless other influences.